Assalamu alaikum, everyone. We're going to go ahead start it in a little bit. Looks like just 2 people have joined so far, so we're going to give people a few minutes to get started. Mute yourselves so that any unnecessary noise does not come through. And then you're welcome to jump in. If it's a smaller group, we can keep this interactive. So people who join on time, I don't want to penalize them, so we're going to go ahead and get started. So welcome to the FAST Alumni North America's webinar series. We did our first one last month, actually back in March, on entrepreneurship. This is the second session. This was scheduled for April, but because of some logistical reasons, we moved it to early May. We may have another one end of May or early June, which will be a follow-up from this one, and we will be covering in great detail the actual implementation use case study from Walmart. So Hamza Farooq, one of the alumni who works in the Walmart's data science team, he has been doing some remarkable work with predictive analytics and AI in the retail space. So he will be covering some specifics and detail level implementation type of stuff in a follow-up session from this later this month or early next month. Then we are lining up speakers for subsequent presentations. We are trying to do this once a month. So this is part of the alumni organization's initiative to get a few more activities going. FAST alumni organization has been focused on collecting funds from alumni and then distributing those funds on a need basis through scholarships to needy students in all the campuses of FAST in Pakistan. But now we are extending that charter of the alumni organization to include more webinars, training, research collaboration, networking, and entrepreneurship. And you will see more activities happening in all of those directions. So with that, I'm going to go ahead and get started. So this is a presentation about artificial intelligence. What we are looking to cover is the basics and fundamentals of artificial intelligence in various different areas. It's a very hot topic. All sorts of industries and sectors are getting impacted by progress in AI methods, techniques, and applications. So I'm going to be providing a high-level overview just so that people understand where things are and how they are different or overlapping one from the other. The space is changing very fast, and the definitions and the concepts, I'm trying to keep them at a very high level and at a logical level. Individual implementations will keep on evolving. So basically, right now, the hype around artificial intelligence is all over the place. Video games, that's a huge industry. A lot of gamers, a lot of very addictive and sophisticated games with gaming technology behind them is a big growing sector. So Netflix, in their recent quarter, even though they showed growth, but they said the competition is not coming from HBO or other TV or entertainment content providers. The competition is coming from gaming. So gaming is a real media entertainment giant now, and it is heavily influenced by artificial intelligence. And I'll share a few examples, methods, and progress that has happened. Same is with self-driving cars. That's also a big area of focus for the entire automotive and transportation sector across US and Europe. All the car manufacturers are jumping into this and moving towards this initiative. And so we will be covering that a little bit. Then robots have been there in factories for a number of years. Now they are trying to get robots to do other advanced things, and we'll see what are the underlying components and how they apply. Talking computers is just a broad term I'm using to refer to Apple Siri or Hey Google or Alexa from Amazon, but it is going beyond that. So we will be covering that in a little bit more detail. IoT deals with devices, machines, and sensors, which are recording and reporting information on a state of a device or an operation, and based on that, allowing you to take actions. There are both components of it. The consumer side, in-home electronics are becoming IoT enabled and becoming smarter, as well as in the industrial sector, where this shift is actually a dramatic paradigm shift. We will talk about a little bit about what predictive models are and how they fit into all of this. Similarly, what are descriptive models, how they fit into this. And then we're going to cover a little bit about the mathematics and statistics and the big data and analytics pieces, which are not truly AI, but it's important to figure out where that line is, where mathematics and statistics stop and AI starts. That is the focus of this piece. So this is a little bit about me. So I have been involved with artificial intelligence and data for a number of years. As you can see, the first project we did as an offshore project from Pakistan was back in 1996, which was a pilot scheduling system for Northwest Airlines, which was the third largest airline in the world at that time. And then hosted data warehousing in 2004. Recently, I have done a salary negotiation bot. So an employee coming into a company to get a job, when they negotiate their package, to get all the human biases out of it and get them a fair deal, they actually negotiate their salary package with a bot. Right now, it is not fully voice interactive. There are some clicks you have to do, but we are moving towards making it a fully conversational type of a back and forth negotiation where a candidate can negotiate a package for a given position. And then we'll talk, other work I'm doing right now is NLP, natural language processing. This is the book I wrote about analytics back in 2013, and it covers, provides a detailed methodology on how to go about using predictive models in a real world environment. And some of my startup work, so I have been involved with the AI-based startup initiatives and have been working with those for a number of years. I do not have any formal training in data mining or AI or in mathematics and statistics. So a lot of the things that I'm going to be covering over the last 20 years that I've been doing, we will be covering based on practical experience, hands-on implementation experience. And if there is interest among the audience, we may be able to find, I know of several past alumni who went ahead and did their PhDs in AI. We can bring them on and they can cover some of the theoretical or the academic side of research and development in AI. I am a regular speaker on topics related to this. These are some of the forums where I regularly speak across 3 continents. All right, so let's start with the definition. The reason why I wanted to give this background is that because of the variety of things going on in AI, it's very difficult for one person to kind of keep an eye on what's going on and cover all aspects of it. So I'll try to do the best I can based on the hands-on experience I have with various AI type of initiatives that I have undertaken over the years. All right, so this definition comes from Wikipedia, and all it's saying is that any device that perceives its environment and takes action to maximize its chance of successfully achieving its goal. So first of all, it's a device. So this is what separates artificial from natural intelligence that humans or animals have. And then perception is the other important keyword here. So what you look at here is that perception basically means input and learning. I take this definition and I break it down into 2 things. Perception, which is basically input and learning from it, and action, which is basically a decision, what are you going to do? So the device is going to take an action. Now, in the early 80s, early days of formal AI, there was a clear distinction between a decision support system and an expert system. These 2 terms are no longer in use, but they were the dominant terms in mid to late 80s and early 90s in the field of AI. A decision support system was going to use AI methods, but it would only suggest or recommend a decision that you should do this. But an expert system would actually take the decision. So some of the, in the energy, grid management, utilities, there were some expert systems that were put in place that would actually take automated decisions. These days, the AI is moving more towards executed decision, which means that the system is going to take the decision itself based on what it sees as the input and learns from it. So essentially, we are simplifying the definition of AI to allow a device to take a decision on a given set of variables. The reason why, so the decision and the variables are two very important terms, and you will see in a second why I'm kind of simplifying the definition down to these two terms. The reason why you see an asterisk there is that a lot of the speech related interaction, conversation, debates, and all of that computers are doing does not really fit into this definition. And I was not able to find a better definition for that. So we're going to leave it at that. And once I explain the difference between the two, then you will see how they come together. All right, so this is not very different from if you are looking to buy a cell phone. The variables you would consider would be the price, the brand, some of the features that you're interested in, warranty, etc. Those will be your variables. You will evaluate various phone or devices available in the market based on those variables, and based on that, you will make a decision that, okay, I'm going to buy this particular phone. So this decision versus variable is not something unique to machines. Humans do it all the time, from pulling out your car from your driveway or garage to walking down the stairs. You are taking decisions at every moment, and some variables are being considered. You're doing it so fast and automatically that you don't recognize it, but decisions and variables are in every aspect of our daily life. All right, so I also wanted to separate visualization from a lot of this. Visualization has nothing to do with AI for the most part. It is just a form of reporting. So it falls into the BI space, business intelligence space, and not necessarily into AI space. And the reason why that is important to distinguish is that if you see this picture, this is from a not Star Wars, the Iron Man movie, and what Iron Man is really doing is there were bomb blasts that had happened, and it asks its computer to plot them on the intensity of the bomb explosion. So the red lines that you see is the intensity of the bomb explosion. And what he's really doing is that he is analyzing the data himself, and he's trying to figure out where is the interesting piece or bit of information. The machine is not telling him what is of interest. So that distinction right there separates AI from a visualization or business intelligence and reporting type of methods or techniques that are out there. The line is blurring, but we should continue to distinguish between these two because the implementation details of one from the other is dramatically different. All right, so is this just a hype? Is this like something that we have just uncovered, and just like other technologies, is this going to go away in a few years? That is, so if you are looking to invest as an investor, as an entrepreneur, or as a student in your career in this area, is this a long-term thing or is this a short-term thing? So I think it's very important to understand that distinction. So take a look at this statement. This statement talks about smart machine or smart instrument. So it says, suppose every instrument could by command or anticipation of need, which means the instrument figures out that I need to run, I need to execute its function. So this statement actually sums up in a very succinct way what we are really talking about here in terms of smart machines. This statement was actually given by Aristotle back in his days, 2,500 years ago. So that means that he could see this back then, that these instruments will become automated and smart and will take action on their own. So all we have done is evolve towards that vision, and therefore this artificial intelligence or this smart machines driven world is a reality that we have to learn to live with. So this is a natural societal evolution. It's just a step in the natural societal evolution, and the evidence is that he could see this 2,500 years ago, and we are only now trying to get it implemented and observe and experience in our daily lives. Similarly, there is an excerpt from an article here which talks about application of statistical and mathematical methods to decision-making problems. This article came out in Harvard Business Review in 1958, and what they were saying was, back in 1958, they were saying that in the 80s, this will already be in place. So it didn't happen in the 80s, didn't happen in the 90s, it's only now happening and it's becoming dominant. So unlike e-commerce or ERPs or the smartphone revolution that had a very dramatic start, a revolution, and then kind of tapering off, unlike that, this space is actually going to continue. That's why I wanted to highlight this aspect, especially since I'm talking about these more from a commercial, business and practical standpoint. So this is a reality for organizations. This is a reality for workers that they will have to deal with this in the coming decades. It's not a fad that's going to go away. All right. So let's take a look at the AI landscape, all these various types of activities. How do they fit in? So this is some ongoing research I'm doing with a couple of professors that we are trying to simplify the implementation details. So we have come up with this approach where on the horizontal axis, you see the cognitive complexity. So what that really is, from walking down the stairs, your cognitive complexity is very, very simple. Just a couple of things you're keeping an eye on and a handful of variables you're dealing with, and based on that, you're making a decision. So if a machine does that, so on very few input variables, if it takes a decision, then the cognitive complexity is low. And if the variables are very, very complex and the decision-making process itself is extremely complex, then you're looking at high cognitive complexity. So for example, low cognitive complexity for some of these initiatives is like monitoring. If you're simply monitoring a threshold, so if the meter reading goes above 100 degrees or something like that, the machine needs to shut down. That is an automated decision that qualifies to be in AI, but it's very low cognitive complexity because it's probably just looking at a couple of a handful of variables and making a decision. Then you move into more like reporting driven initiatives where you have a little bit more complex situation that you are taking a decision on. That's how we typically look at the metrics or KPIs in business. Then the equations. So equations are, they can handle a much wider variety, especially if it's like a quadratic equation or something like that. It can handle the number of variables that it can easily handle, and their time series impact is much larger, so your cognitive complexity increases. Because the decision is being made on an equation. It's not just if the meter reading is greater than 100, do this. No, it's like an equation. You plot that in an equation, you calculate some derivatives or something like that, and based on that, you decide what decision is going to be taken. Then we move into what we call models. So AI right now, predictive models or descriptive models, all the hype is around models. And we will talk about that in a little bit more detail. Then higher level of speech is far more complex than models. And then strategy. So you will understand these once we use some examples. Similarly, on the left-hand side is a data continuum, data and information complexity. So at the lower level, the telemetry data, which is just basically some kind of logs or sensors reporting their status or signals coming out of devices. And then transactions is more like you buying and selling stuff, the structured data. Then you move into big data, which is nothing more than the scale and volume, velocity and volume, size of the data and speed with which the data comes in. It starts to qualify that in the big data realm. That's where you start to move into more complex data sets, which are variables. And then finally you move into rules. So this is kind of, on the left-hand side is the data complexity and information complexity. Right-hand side is the decision complexity. So on the left-hand side, you're getting your variables. If you remember, the definition was decisions on variables. So right-hand, the horizontal axis is decisions, and the vertical axis is variables. So IoT, which is the smart devices, they kind of fall in here. They are based on predictive models, but they are using very basic data sets, and their data sets are fairly atomic. The volume is large, but still manageable. And so they are kind of in this lower tier. On the other hand, when we build risk models for credit cards or home loans, which is something that I have been doing a number of years, they kind of fall here, where you do start to deal with a little bit of big data, and you definitely need predictive models for this to work. Then talking bot like a Siri or Alexa, they kind of move up a little bit. And then debating bot is extremely complex. There have been some remarkable breakthroughs in that space in the last 2 years, where a bot can actually understand your argument and provide a rebuttal to your argument. So that is just remarkable achievement of where these technologies are now going. Gaming is also up there, especially the more complex strategy type of gaming, where you are not playing against other people, you're playing against the computer, and they continue to evolve and become more sophisticated. So when it comes to strategy, you are actually looking for an end state. There is an objective. You have to win the game. You have to score more points, something along those lines. That's where the strategy kind of comes in. All right. Now, self-driving cars, interestingly, is all over the place. Self-driving cars need a lot of data to come through, a whole bunch of visual sensors, and they need a lot of data around roads and turns and traffics and bridges and stoplights. All of that, they have to have that data. So their data space is all over the place. And similarly, because they have to reach their end state, so from their starting point to their ending point, they have to understand strategy, slow down, speed up, take a turn, take a shortcut. All of that has to be done by the machine itself. So it actually uses all of these. So you can see why self-driving cars is not only a very complex project or task, but it also involves a whole wide variety, and therefore, like multi-billion-dollar investment is kind of required to get started on this. All right, so this should give you a little bit of an overview, and now we're going to go into specifics. What is a model? So this is the most important part. This is the foundation on which AI and AI-based decision-making or AI-based rules or strategies are built on. So there are two forms of models primarily, deterministic models and non-deterministic. Deterministic models you are all familiar with from the 7th grade, you are 6th or 7th or 8th grade, you are exposed to this. All you have is, you have a series of points, you draw a line through it, you convert that into an equation, and now for every value of X, you have a value of Y. This is a deterministic model because there is no gray area. Whatever value of X you're going to put into this equation, you will get a value of Y. So if X is the input, Y is the decision, then your input and your decision is fairly straightforward if your problem fits this equation. And there are a lot of problems where it does, like the Charles' law or Boyle's law or Newton's laws. A lot of those laws are actually deterministic models where you provide the input, you get the output, and output is basically your equivalent to your action. You can have a little bit more complex model, but still it's a deterministic model. And for given values of input variables, you can get the independent variable the dependent variable will give you the action. So you need a series of data points, and your equation is actually a model, but it's a deterministic model. Once you build the model, once you build the equation, any new input will give you a new output. So you don't need to know all the inputs upfront. Once you build the equation, then input and output process can be done automatically. And if you have a machine that is doing this, then it's, in my definition, that doesn't quite fit into AI, but some people may argue that it's actually AI. So, however, but the deterministic models are more mathematics and statistics based and not computer science based. All right. Now, non-deterministic models, they are the models where a gray area, certain degree of uncertainty is also involved. So, yes, for a given value of X, you have an equation, but then you have a probability function with it that, yeah, there is a likelihood that this could be the output. So once you introduce a gray area into an equation, then you are dealing with a non-deterministic model, and probability has to be in there. So statistics also handles this. This is an example of a regression model equation that I built, I don't know, 10 years ago. So statistics also does that. But computer science really took it to the next level. So actuarial science, econometric, informatics, sabermetric, all of them in the 60s and 70s have done a lot of work in non-deterministic models, probability-driven models where certain degree of gray area is involved, and you are not certain what the output will be. You just have an idea. But AI has really taken this to the next level using very different computer science-driven techniques and methods like neural network or decision trees. All right, any questions to this point? Okay. So as I said, there are deterministic models in algebra and calculus and statistics. There are non-deterministic models, AI, in particular, predictive or association rules. Then there are also descriptive models. These are discovery models. So visualization kind of falls in there, but then there are clustering and link analysis type of or NLP type of discovery models that are different from both deterministic and non-deterministic. And we will briefly just cover that, go over that in a little bit. And then, of course, there's deep learning. I don't think I will have time to get into deep learning. All right, looks like there is a question or no. All right, so we'll keep moving forward. So here's how to build a model. How does AI actually build a model? Here is a simple example. So let's say this is your entire data set. What it does is that it learns from historic data. It figures out a pattern, and then it uses that pattern for subsequent future decisions. Unlike an equation, we train the model on learning data, and then we use the model we provide new inputs, and it gives you output. So this is a simple data set, which I will use as an example. So you have age of an individual, you have their income, whether they are a student or not, their credit rating, and then if they buy a computer or not. So if you just look at if this was the entire data set, which has 4 input variables and about 15 or 20 records. If this was the entire set and I ask you to, can you see a pattern? When does somebody buy a computer? You can probably just eyeballing it, figure it out that, yeah, this is how somebody would buy a computer. If they are age 31 to 40 and their student status is yes, they may actually buy a computer, something like that. So, but when you are dealing with 20, 30, 40 variables and millions of records, then it is not possible for you to eyeball it and figure out what is the pattern where typically somebody buys a computer. So that is where we allow artificial intelligence methods to take this data as input and figure out when somebody is going to buy a computer. And the 3 known most popular techniques are the Bayesian network, neural network, and decision tree. Now, those methods are out of the scope of this presentation, and the decision tree is the easiest to explain, so that's what I typically try to use. So this is what it's going to do. It is actually going to build a tree, a decision tree out of that sample data. So what it found was that, okay, if the age was less than or equal to 30 and it was a student, yes, then the computer buying is yes. And if the student was no, then the computer buying was a no. So from the sample data, it will build a tree like this. And it will, this is called the model. Now the model is trained, model is ready. This tree is going to be sitting behind the scenes in the code in the AI model. So let's say a new customer comes in we will ask what's your age, and we will ask what's your credit rating, and we will ask whether you are a student or not. We will provide that as an input to this model, and it will tell us whether he is going to buy the computer or not. So if the person was age 35, then it'll go into the center line, and it will immediately determine that I don't even need to know the other questions, he will buy the computer. So that is how a model is trained, and once it's trained, this type of a tree is built in. Similarly, in neural network, a different type of a picture will occur, but that's the process where from existing data, it tries to figure out what is the pattern when somebody does something or does not do something. So here's an example. So this is your historic data. From that historic data, you know whether they bought the computer or not. So you already know that. And this last column is called the predicted variable. This is the one you're trying to predict. And in the historic data, you know the values, so you learn from that. So now you pass a decision tree algorithm, which is a standard algorithm. It doesn't care what input you provide. If you provide 10 variables, 100 million records, or 2 variables and 20 records, the same algorithm will run on that data and try to build a model. If it cannot find a pattern, then it will simply come back and say that nothing found. If it does find a pattern, it will say the model is ready, and now you can test it or run with it. So that's what a predictive model is using the decision tree method. You can have a neural network model as well. The algorithms are fairly standard. The techniques, how a decision tree is built, there is ongoing R&D and improvement on that, but the technique is widely understood among AI academics or AI students and professionals. Now you have a new data set. So you build the model on your historic data set, and now a new customer walks in. The first one is aged over 40, medium income level, is a student, and has excellent credit rating. But now we don't know whether he's going to buy or not. So what we do is we send that information to the predictive variable. It's an unknown value. We don't know whether he's going to buy or not. He has just walked into the store or come on our website. So then we give that as an input to the model. We supply that customer's information, and the model runs that through the tree and comes back and tells us the output, whether he's going to buy it or not, and is going to give us a degree of probability depending on, because in multiple, that customer can fit into multiple branches of the tree. It's not necessary that you always fit into one branch. Some of the branches can have an overlap. So based on that, the model will give us a degree of probability that it's likely that they would buy or not. So then once you have that decision, what do you do next? So how do you actually transform your business processes? So for that, I've used an example of a IoT of a device. So we build a model that predicts when a device is going to fail. So let's say in the telecom, you have like a tower, and underneath the tower, there is a small computing machine that's sitting there. That's what the tower signals and communication and everything is using. And because it's 2 years old and you haven't done any maintenance on that tower, it's middle of nowhere. So you run an algorithm, you run a model, and the model tells you that, hey, there is a chance that this device may fail. So the model gives you a probability. Now it's up to the business process owner to decide what to do with that probability, because as I said, it's not going to be a certain output. is going to be a probabilistic output. So if the chance of device failure is greater than 87%, this is the left leg of the branch here, then we check for the last maintenance. If the last maintenance was done within 3 months and the age of the device is greater than 5 years, it means that if it's still showing a high probability of failure, then you probably want to replace the device because it's at the end of life, it's done. If the probability of failure is less than 61%, then you don't take any action. And then if it's between 62 and 88, then you look for a nearby schedule, meaning someone already out there in the field fixing devices. If someone is close by, you ask them. So someone is within next 2 days, within 10 miles of that, if someone is going there to make another repair, you add this to the schedule. And if no one is in that area, then you don't take any action. You can't really do anything about it. You got to just live with it. Business always has limited funds, limited budget, so they always prioritize where they're gonna spend that money. So this is how you kind of put these models to work in a real world scheduling or dispatching situation where maintenance crews are going out there. Where do you send them and when do you send them? AI is helping you figure that out. So then the other type of model, so this was a predictive model. So discovery or descriptive model, they work slightly differently. So let's just assume that these are two axes. One is number of transactions and the other is amount of transactions. So let's assume this is simply a credit card data. And number of transactions actually gives you how many transactions you've done, and amount of transaction tells you what was the dollar amount on the transaction. So you plot every single customer's every single transaction on this, and you every single customer on this, and you kind of create this type of a two-dimensional graph plot. And once you've done that, then you hand this over to a clustering algorithm, which is part of a AI method, and you ask the clustering algorithm to create clusters out of it. So what it will do is it will start to move these transactions wherever, whoever is closest to them, they will start to move those dots closest to them. So it will go through numerous iterations and it will slowly start to look something like this. Once it starts to look something like this, an AI-based algorithm is making a decision which plotted points go close to which other ones. And then you start to see these clusters. Once you have these clusters, then you can label them, because they do show some distinct characteristics, the one on the right, and you label them. Because low volume, high frequency, meaning the amount is small, but the number of transactions is high. So that's your LH segment. Underneath is your LL, and then similarly your high volume, high frequency, and high volume, low frequency. So for credit card in particular, most profitable are the HH, because they are likely to get a lot of utilization on their credit limits and probably end up paying some interest. So that's where the banks make money. So the HH segment is actually better for them. If it was the original drawing where all the dots were all over the place, you can't really make any use of it. So you rely on clustering to help you figure out where you're going to go next. How do you classify these people into a group? So that's an example of a clustering method or descriptive model versus a predictive model which works off of probabilities. So now that we look back at this, you can probably understand that, okay, if they are using models, some are predictive models, some are descriptive models. Based on that, these decisions are being made, and the amount of data on the left-hand side is being used in building and testing and training those models. All right, so I'm going to skip testing and tuning because I'm actually going to jump into some of the other areas. So IoT in particular, this is heavily used in smart machines, smart factory operations, self-driving cars. They all heavily rely on this. So they have 4 pieces. For that to work, for if you are going to go build a smart car or self-driving car, you're going to need to deal with these 4 things. The sensor. You're going to need all sorts of cameras and motion sensors and objects in front of you or behind you, how fast you are going, wind, weather, visibility. A lot of those things kind of come into play. So you need to have all kinds of sensors that are actually tracking, recording, and passing information to the brain of the self-driving car. And the sensors start to beep, or the sensors, if the car is too close to the next car, if it's sliding off the lane, drifting into the other lane, when those, or you're going too fast for a turn, upcoming turn, then the sensors have thresholds, and based on those thresholds, the sensor may take an action or may simply warn the driver that something is going on. So sensors are constantly tracking information and monitoring it and measuring it against a given threshold. The moment they go over the threshold, they have to either take an action or they have to inform the driver. The edge network, so this is where you have these sensors in a car. Some are in the tire, some are in the front bumper, some are in the lights. So how do you place them and how do they talk to each other? How do you ensure communication between these sensors does not break down? So within a car, there is kind of a network with hundreds of devices and sensors recording data, and they are interconnected through this network. So network has to be stable, and network should allow communication to happen between these sensors. And then also you need failover sensors. If one of them is not working, then the other one, a replacement or a redundant one, has to be available to continue to provide that input. So you have to get that data and these sensors lined up in some kind of a network, so they are talking to each other and they are able, or talking to a central point, and they are able to send information back and forth. In case of a factory where you have a lot of machines with these sensors, this becomes a little bit more tricky. Because you may have to set up a separate Wi-Fi or a separate wireless within the factory floor for this to work. And then also, a lot of these sensors may not have very powerful antennas because they are a very small sensor. So you can't put a very powerful antenna. So the network router or the network point has to be close to them so that they can communicate and continue to record their outputs. Then there is data processing step, where a lot of these big data platforms come in because sub-second or several times during a minute data is passed. So you need a very stable and sophisticated data recording, storing, and analysis mechanism, which has to be really, really fast. So your data processing is your next challenge in this space. Because image processing itself is a very slow process, even though computing has come a long way. And because the driver or the car has to take a decision immediately, whether to stop or whether to turn or slow down, whatever, the car has to be able to process the images coming from 360-degree cameras. So the cameras are all around the car, and it has to immediately process the images and figure out what is around it. If there is any threat, then it needs to take evasive action. And then, of course, lastly is the decision science piece, which deals with models and rules and strategy. So that's where different types of models are put to work, and a combination of various AI, mathematics, and statistics methods are put to work to allow the car to actually make a decision and then optimize that decision. If it has two choices, it can either slow down, hit a brake, or swerve out of the way into the next lane or something like that. Which decision it's going to take, that kind of gets into this decision science. Now, big data is one of the areas that within this space where you have sensors and a lot of Internet of Things, IoT, where sensors are on every single machine and they are constantly recording data, so you're dealing with a lot of data set. So this is from the actual project that I did over 4 years, and I dealt with 10 million smart meters. the last line of this table. And if you look at the size in GB, you look at 41,000, so that's about 41 terabytes of raw data, and 1 trillion records from 10 million smart meters were coming in on a 3-year, if I store them for 3 years. So that's a lot of data, that's a lot of volume, but so there are no data errors in here because machines are sending this data, it's not humans typing stuff, so there are no mistakes. Yes, you can get erroneous censor, which will send you large data sets, but there are ways to control that. It can set negative values or very large numbers or something like that. And this is structured. This data is very well structured, typically a smaller structure. So this 41 terabyte is 1 trillion records, which is overwhelming. But if you look at it, it's 41 terabyte of raw data. And if you do a basic compression, because the data is so similar, the compression algorithms work really well. You can store it in 4 terabyte. And if you actually summarize this data for analysis purposes, then you will get it down to 400 GB. So even though it is a lot of data, but if you really sit down and think about it, it's not as complicated as it would sound originally. And cars do process this kind of volume, self-driving cars, on a regular basis. So the computing machinery that they're putting on self-driving cars is actually very, very sophisticated now. I'll skip this part and I'll jump into opportunities. All right, so a lot of these things that we just talked about, if you look at this diagram or this picture, there are 4 circles here. The innermost circle, which is just calculation or computing at the bottom of everything, this is what we're talking about, the 40s and the 50s, when computers came about and they started to tackle very large computational challenges, calculations and linear algebra type of stuff. And a different type of methodology to develop and deploy that software and that hardware was used in that innermost circle. Then in the 60s and 70s, in the 70s in particular, you started to get into operational systems where you started to automate the business, workflows, any paper that was moving was digitized, and a different tool set, development methodology, programming languages, all of those kind of came about as it evolved beyond just computing. Then in the early 90s, we went into business intelligence because now we had been digitizing data for the last 20 years, for 15, 20 years at least. So they all of a sudden had a lot of historic data at their disposal, which business intelligence then started to use, and data warehousing and a lot of these concepts, very large databases came about. And but again, the tool sets changed, and the development methodologies changed, and the programming frameworks changed. New things came about, which allowed you to handle that. And now we are in this business analytics phase where a lot of these AI-driven models are actually transforming what you can do on top of that data. So if you remember the original diagram we did, on the left axis was the data axis. So with business intelligence, we traversed that axis about halfway, and now with AI, we are kind of getting into the higher end of this complex data and information set. So again, the tool sets are changing, the development methods are changing, but it is all part of the same evolution, and as we move from one to the other, it's a continuum. So nothing should be surprising what is happening. It was bound to happen, and this diagram I think I put together in 2006. It was evident that this is where we are heading. And this impacts, if you see, financial, sales, marketing, operations, HR. So this actually impacts everybody. It's not just one or two teams or professionals or only people working in automotive get to see this. This is impacting everything. Whatever you do, you have computing, you have basic automation, you have some reporting, and you will have AI involved in every function that you do on your on a daily basis in business. All right, so here's a quick anecdote to kind of illustrate. Well, actually, I'm over time. what do you guys think? Should I go? I will take another 20 minutes to wrap it up, but we started late as well. So if you don't mind, I would like to keep going, and we are recording this, so we still have time on our recording. So here's a interesting example to help you understand where the priorities need to be. Okay, so it looks like everyone is suggesting we keep going. All right, so this is just a simple story to illustrate a point. So a customer or traveler advocacy group, they used some data scientists and some AI methods and looked at a lot of data, and they came up with a conclusion. And they said there is a high probability that every 10 millionth flight will have one of the pilots drunk. Now, on a yearly basis, there are about 2.5 million flights that take place. So then once every 4 years, at least you will have one situation where a pilot is drunk. And so they raised that as a red flag. So when that study and that conclusion came out, then all the airline executives were worried about it, regulators were on them, and the customers started to cancel their flights, and all sorts of things started to happen. So the airline industry says, you know what, we need to counter this conclusion. So we will hire our own team of data scientists, and we will challenge this conclusion. So they hired their own data scientists, and their data scientists went to work. They bought the best technology and all the data, and they worked on it. And they said that actually the conclusion is correct. However, there is hardly any chance that a flight has both pilots drunk. So what they recommended is that you ask mandatory for one of the pilots to consume alcohol before flying. So it's a slight bit of humor here, but the point I'm trying to make with this is that the job of the data scientist or job of the people working with the data, working with the models, is not about technology and not about the technique. It's about what do you do with it. And that message is missing on a lot of the training and certification and courses that I'm seeing. Nobody is emphasizing putting AI to work. They are emphasizing building AI. And these are two totally different things. One you can actually learn fairly easily, relatively. The other, the adoption or the application, is far more complicated. So with this conclusion, it's not the technique that the airline AI experts used. The technique was fine. The technology was fine. It's really coming down to what is the conclusion you're drawing and whether that conclusion makes sense or not. All right. So typically, there are two areas of innovation or entrepreneurship growth ideas. One is innovation. So you have Apple, Sony, BMW, designer clothing. All of that is innovation. And there is human creativity and element of art in there. Then the other aspect is process innovation, where operational excellence and customer intimacy are essential. So AI and data science focuses on the bottom part far more than it focuses on the top part. But it is kind of, with the speech and gaming, it is entering the top part as well. But for the most part, it is, you look at an existing process, there is computing going on, there is automation going on, there is business intelligence reporting going on. So there is need for AI in that process. That's kind of almost automatic. All right, so let's talk about gaming real quick here. So this is an example of how gaming algorithms used to work and still working for the large part. So this is a game which is algorithm which is trying to figure out the tic-tac-toe. So tic-tac-toe, the top picture shows you the current position and its X's move. So X has 3 possible moves, and then based on each move, the O will move, or the 0 will move, and then X will move again. So what these algorithms do is that given a position, they actually build this type of a tree of all the available options and what will do next, what will happen next, and what can happen next. They actually compute this entire tree on every move, and based on that, they then figure out which moves make more sense, and that's the move they take. So the one on the right is a move that they are going to make based on this. Okay, actually, this is a good point. If I let me manage the participants and unmute. Everyone is unmuted, so you should be able to ask a question.
Yeah, I was just able to unmute myself. Can you hear me?
Yes.
Okay, this is Ahmed Malik. I had an overall AI question, but we could talk about it once the presentation is over. And it was more about how do we identify the first use cases for AI in an organization, because organization have no idea about AI. We as an IT people need to educate them in that. And I think the number one step is to identify some use cases, and most probably it is in the context of data science. So just wanted to hear your thought about it.
Okay, so I can cover that towards the end, because yeah, because this is more of a content for Hamza's presentation, which will follow this one. He is covering that in a little bit more detail, so I can cover this a little bit. So, but I'll continue with this. So this is how gaming algorithms used to work. That chess is the same way, tic-tac-toe the same way. They will actually compute all the subsequent possible positions. Based on that, they find the end state that they like, and then they come back up and they figure out what is the move they're going to make. This was the dominant method for building gaming algorithms, where you play against a computer in any game for almost 2-3 decades. Then something different happened lately, just a few years ago. And that's a dramatic breakthrough. This was a well-established method. They were just improving the optimization and tuning of this. And the chess playing computers that have been beating world chess champions use this type of an approach. Now, Alpha was a project that a 3 or 4 man startup that actually created a different method of gaming, which has actually revolutionized this. And once they broke out, they did a news conference, they explained what they had done. Within a month, they were bought out by Google. So Alpha, what that does is that Alpha does not follow an algorithm which is designed for a particular game. So if a tic-tac-toe algorithm is used, same software is asked to play chess, it's not going to know what to do, because the moves are far more complex, the tree goes much deeper, the type of pieces in chess, different types of moves, the knight moves different than a bishop, all of that in tic-tac-toe you couldn't handle. What Alpha did was that they built an algorithm which plays with itself. So what it does is that Go is a Far East game, very popular in South Korea and Far East, and has far more computations, permutations, and combinations than chess. And it was until 2 years ago, it was assumed that computers may not be able to beat a Go human champion because the strategy and decision making and all of that was way too complex. So what Alpha did was that they created this algorithm and it played with itself. So it played with itself over 10 million games in a few hours. And from each game, it learned what to do, what not to do. Because if it lost, or if it lost a piece, if it lost a position or something like that, it kept making a note of it. Oh, okay, I shouldn't do this. Oh, okay, I shouldn't do this. So every time it would lose, it would learn from it. And it'll come back and improve. It'll come back and improve. So after playing 10 million games, it was playing at a master level. So then they challenged the world's Go champion, and alpha was able to beat that individual. So what they did then, they did not rewrite the software. They just input the chess parameters as to what is a good move and what is a bad move, with some position calculus, with some pieces definition, and the end goal of how to win. So the same software was then taught chess. It played with itself for 8 hours non-stop, and it was like chess rating. I'm sure you've heard of it. There's like a kids typically who start playing are 300 or 400 rated, and then they keep improving. At 1800 rating, you become a master. At 2000, you become a grandmaster. And I think the current world champion is 2600 rated or something like that. So alpha was playing with itself and learning from its mistakes, and it started to, after just 8 hours of play, it was already at the master level. It was playing at the 1800 rating chess already. Along the way, a couple of very interesting things happened. Not only did it beat the world chess #1 software, which is the leading chess software in the world, alpha beat it. That software was built specifically for chess. Alpha was not built specifically for chess. And the other interesting thing happened was that it started to, like, it would take its king out into the opponent's area and fighting all over the place. If you do that, if you move your king to the front lines, if your chess instructor or your coach will just slap you. Hey, don't do that. Don't ever move your king outside of this. But alpha had no such conventions that it needed to follow. So it just computed what will work, and based on that, it made moves that baffled the chess experts when they looked at the games later. They were just baffled that how the hell did it see this type of a move and how it changed the game entirely. So this is a revolutionary breakthrough where it's dangerous as well, because you don't know what it would decide. If you give it a parameter, okay, you have to win this game this way, it may take a direction which is not good overall for the game or for the players, people's safety. All kinds of things can get involved if this method is involved in military or in law enforcement, because it will not follow conventional wisdom. It'll just focus on the goal or the objective, and it will achieve it however it sees fit. The other one I want to cover is the stalking bots. So you are aware of the response conversation, that Siri and Alexa type of where you ask a question, they give you an answer, or you ask for an information, they pick up that information. They dig up that information and provide it back to you. So that is fairly stable, doing really well. A lot of companies are coming out with these type of products. They are used in therapy, where they are interacting with patients with different depression or psychological problems, and the therapy, the speech therapy or psychotherapy is being done by these type of bots. They don't get tired. If you want to call them in the middle of the night and want to talk to them, they are available. So it's actually very cost effective, and the results are actually phenomenal. One of the things I did last year was a salary negotiation bot. So it's not fully speech enabled, but it does interact with the candidate, and then with some press of a buttons, you can actually do a salary negotiation with a machine. So individual biases are removed from that equation. But the major breakthrough came late last year or mid last year, was about debate. And that's where these talking bots are actually understanding your argument and are rebutting it. So if you're saying that there should be tighter gun control, or a country like Pakistan should not be moving towards democracy, something like that, you come up with an argument, it will actually provide a rebuttal. And they did several tests. You can Google this and look at some of these phenomenal achievements that these talking computers are now able to do. And this is just a remarkable breakthrough. And that is about all. So we will now open up for questions. the purpose of this presentation, as I had originally stated, was just to kind of make sure that I provide an overview of all the moving parts, or most of the moving parts, where there's a lot of hype these days, and then we can go deeper into a few things and provide you an overview so that you can continue to do your own research on your own if some of these things are interesting for you. All right, so any questions? All right, so in case we don't have any questions, we will, there is, you are all muted. Hold on, let me figure out. All right. I am pressing the unmute all, but for some reason it's forcing me to do it manually one by one. All right, go ahead.
So again, my question is, what are some of the use cases that you see people starting with? Okay, so the way I would address that is that what you want to do is, let me get to this picture that'll illustrate that. All right, so the idea here is that you're probably already doing a lot of reporting. You have business automation already in place, and you're probably doing a lot of reporting on certain aspects of your business. And most reporting is typically focused on aspects of the business which are important. So the sales, marketing, finance, a lot of those are typically far more important versus facilities management or some other corporate expenses and stuff like that. Travel expenses are much lower in priority. The executives are always looking for reporting on stuff which is important to them. So my advice always to organizations and professionals is, wherever there is focus on this business intelligence circle, wherever they are looking for more data and more information, that is where you start to figure out, can AI help? Can I do something? So if they are looking at month-end numbers, for example, some kind of profitability numbers at month-end, you can give them that number through a forecasting algorithm or using some predictive methods, and you can give them that number 5 or 8 days in advance, or maybe a month in advance, if it's a quarterly number or something like that. So you always start where organization already focuses on, and you look at the data that they are reporting on, and that is where you formulate a use case that, okay, let me see if AI can help with this to move along this continuum. So you're computing everything, you are digitized, you have your business process flows already working, you have your reporting working, then the analytics or this AI should also follow the same structure. Okay, that's good. So it looks like one participant is trying to unmute herself, but it's not happening. So it happened. I was able to unmute myself.
I am actually trying to unmute everybody. Not sure why it's not working for some. And
okay, I think Sadia, you had a question, please. I think you're able to unmute it. I think everybody is unmuted now.
Yes, I am. My question was basically on your startups. You mentioned before that you had a gaming startup as well in the beginning of the slide. If you have the time, can you tell us a bit about that?
So it's not, I mean, that's just, I'm not a gamer. It was just a personal decision. My kids do a lot of that. So somebody came and they were looking for some NL, natural language processing and text mining help. So once I understood what they were trying to do, I decided to become an advisor as well as an investor. So it's not like I did not start that, it's someone else's initiative. I am just involved with some investment and some advisory capacity. They are basically, because a lot of the work I'm doing the last 3 years has been focused on natural language processing. They were looking for in gaming chats, people are abusing other people, and there are some predators like child predators, because kids play a lot of these games. Those type of things the gaming companies are looking to detect from the chat as to what type of conversations are going on between members or players. And if they see something, some bullying going on or some inappropriate discussion is going on that the gaming company could be held liable for, they want to detect that. So it's not truly a gaming company as such. It's more like making games and game playing environments more safer.
So do you see these voice conversation being analyzed using some kind of sentiment analysis and being used as an input variable for modeling? Is that what you're referring to?
Yeah, so we are classifying them. So you look at a line of text, especially in the chat. Gamers do a lot of chatting. I mean, they do voice as well. We are not focused on voice right now. Only the chatting, gaming related chatting. And from each line of text, it's a little bit beyond sentiment analysis. We are trying to figure out if something inappropriate is being said here, and then we look at a cluster of that chat. So it's a combination of some clustering, combination of some text mining and predictive modeling. And what we do is we provide a risk score on every line of text that someone has written. Hey, is this a high risk test that someone needs to monitor, or do we need to analyze this further? So the methods I had developed for anti-money laundering or for fraud detection, I'm kind of using the same, because you are looking for a negative transaction.
Okay. Thank you.
All right, any more questions? All right, then we will wrap up because this is being recorded and this will get uploaded on YouTube so people can see that and if they want to follow later. And we will continue to communicate on the follow-up session where we will be doing a much deeper dive into specific use cases from the retail sector using Walmart as an example. And one of the FAST alumni will be presenting how to build models, probably covering a little bit more in technology and techniques. All right, thank you, everyone.
Thank you for hosting.